Welcome back, everyone. In this session, we're going to go into gradient boosting. Gradient boosting machine is another name for it. But before we go into that, just want to do some recap. And basically what we've covered so far is bagging or bootstrap aggregating. This is really sampling with replacement. Basically, you combine the average of the output in the regression setting, whereas in the classification setting, it will be in the form of voting. Boosting is where we are in right now. Essentially, the whole idea is to train weak classifiers and then add them to a final strong classifier by weighting. You weight them by accuracy typically. Now, once it's added, the data are reweighted. Misclassified samples will gain weight, so we are learning from those that we have made mistakes on. And those correctly classified samples, we put it aside or reduce the actual weight itself. Now, the algorithm or the machine learning algorithm are essentially forced to learn more from misclassified samples. So you can quickly see the attraction and the intuition of this is such that it's very similar to how humans learn, where the subject or the content or the topic that you are weak in or make a lot of mistakes, you spend more time in that area to learn more and to improve on that. Now, in the previous session, we covered a little bit of bagging, and essentially we went into depth on ADA boosting or adaptive boosting. I mentioned before, it is similar to human learning. It learned from past mistakes by focusing more on difficult problems. And how did actually ADA boosting work? You fit a sequential or sequence of weak learners, and the prediction are combined through a weighted majority. Then what you have is a boosting iteration consists of applying weights to each of the training samples. And initially is equal weighting. For each successive, the sample weights are individually modified. And how do you actually do it? Basically, those that's incorrectly predicted, the weights actually get increased. That means more emphasis on those that you made mistakes on. And for those that are easier or those that are predicted correctly, the weights will be decreased. So as each iteration proceeds, examples that are difficult to predict will receive ever increasing influence. So that's really the basic idea here, and this is adaptive boosting. Now in today's session, the other thing that we did actually do before we go into today, now ADA boost can be combined with random forest classifier or the classification and regression tree, as we did last time. Okay, and so hopefully that actually provide you with some background, and hopefully you can remember that. In this session, we're going to go into gradient boosting machine in a little bit more depth. Now, like the others, like ADA boost, it works for both regression as well as classification problem. Now, the basic idea is that it sequentially add predictors. So it's a little bit different from ADA boost. In this case, it adds predictors bit by bit. Okay, it doesn't actually, not all predictors are being exposed to actually use to actually predict the outcome or the target variable. Each one correcting its predecessors, and you fit new predictors to the residual errors. Now, hence, this is the part that's a little bit different from ADA boost. ADA boost actually, you alter the instant weights, meaning the area that you made a lot of mistakes, you increase the weight. So adding focus in those areas that you make mistakes. Whereas gradient boosting machine, the focus is in the residual errors. So you apply a model or predictors to predict the actual target outcome, and they will explain some of the variance. And what's left, there are some residual errors that's not explained. Then you apply another predictors to it, and you keep going until you actually get to the final predictors that you have. So let me show you these steps that I've prepared, and in terms of the step-by-step process. So the step one, it looks like this. This is, I guess you can say, a simple linear regression. Y is equal to mx and then plus whatever the error term is. And step two, with the error term, right, you use another predictor, which is gx here, okay, essentially x is our predictor. It should really be x2, but that's okay. Another feature, and you apply another function to it, and that leaves you with leftover errors. So if we substitute 2 into 1, replacing these e with these, we get this formula, which is y is equal to fx plus gx plus e2. Now by now you probably can guess what's to come. In step 3, we again arrange or design another model. We model the actual fluctuation of e2 or the behavior of e2 with another function called hx, and whatever is left over that is not modeled with hx, we get e3. Again, you substitute this into this, and what you get is y is equal to fx plus gx plus hx plus the leftover, which is e3. You can keep on continuing on this way until you use up all of your predictors. And finally, we add weighting to each of these functions with alpha, beta, and also a gamma. Now, the key thing with gradient boosting machine is this. It involves 3 elements. The loss function to be optimized. The loss function depends on the type of problem being solved. In the case of regression problem, mean square error, which we've seen before. And if it's classification problem, logarithmic loss will be used. In boosting, at each stage, unexplained loss from prior iterations will be optimized rather than starting from scratch. And that's really the idea here. The unexplained loss, which is the error term here, will be optimized, okay, and instead of starting from scratch. Weak learner to make predictions. Now, decision trees are often used as a weak learner in the gradient boosting, and additive model to add weak learners to minimize the loss function. And trees are basically added one at a time, and existing trees in the model are not changed. The gradient descent procedure is used to minimize the loss when adding the trees, hence the term gradient. Okay, so that's really the whole basic idea here is the gradient boosting machine. So what we will do now is let's do some coding. Now we continue on with the Titanic data sets that we have. So this is from this, we downloaded before, and we're just going to use the same set of features that we have. What are the features? The passenger class, their gender, and finally their age. All right, let's start by importing from the ensemble. From sklearn ensemble, you import the gradient boosting classifier. GBC, this is what I will call it. Fit is equal to the gradient. I'm gonna just leave it as it is, as the default, without actually setting any parameters. This is just our baseline, and we're gonna run our model and fit it into X train and Y train data. And there we go. So the criterion here is Feynman mean square errors is obviously other loss function to use, but for now these are what's being provided. A learning rate is 0.1, so these are basically our benchmark, our base, before we actually develop further. From there, the number estimator is 100. So let's just print the score, and again, instead of typing the whole thing, we're just gonna copy this whole lot. Yep, print the score. Okay, but in this case we have GBC is our classifier. I should really call this COF, so classifier, not fit, classifier. Okay, that's better. So classifier. Okay, so let's run this. Okay, we have an extra comma and an extra bracket. So let's run. Okay, the accuracy rate is 94%, and the average accuracy is 79%. Now, to help with our memory again, let's have a look at our bagging example earlier. Let's just say, see the decision tree is 77. Okay, so 79 is definitely an improvement, and the actual standard deviation has also gone down as well. So that's looking really promising. So let's have a look at the actual test data. Let's see if we have indeed improved out of sample as well. with unseen data. Right, 78%, it's our final result. And if we look at the decision tree that we did as our benchmark, the accuracy score is 76. Here we have 78. Is clearly an improvement over decision tree. Finally, after having looked at so many models, so many different models from random forest to bagging, and finally when it comes to decision tree, come to gradient boosting machine, it's finally outperformed against our basic benchmarks, and in fact it actually outperformed against all of the different models that we have used so far. Okay, what I've done here is that I've consolidated all of the scores here, and for us to actually compare them all. Right, so just so that we can actually view that in one simple or one consolidated place. Now, I will not pay too much attention with the training accuracy score, which is the top line here. I mentioned before, the critical part that we are interested in is the average score and not just a point estimate, because point estimate can always mislead you. Looking at the average accuracy score, decision tree is 77%. Bagging has improved that somewhat. Random forest actually outperformed the decision tree, but for some reason the optimized random forest actually did worse. But I'm feeling that's because that it is actually too optimized, and essentially what you have is a case of overfitting. Right, so which is 59, so that deteriorated substantially. Extra trees didn't really actually improve on the score. Error boost managed to actually match the performance of decision trees. Error boost on random forest also didn't perform as well. But the gradient boosting is actually the best of the lot at coming in at 79%. The standard deviation, it's for decision tree is 10%. Bagging, it reduced that somewhat. Random forest actually has increased variance. Optimized reduced it somewhat, but it's the actual reduced variance is mitigated by the accuracy. Extra trees, variance also quite high. Error boost for the classification and regression tree didn't do much better at 11%. Error boost random forest has dropped substantially to 8.8. But I guess the whole package you can say here is gradient boosting, whereby it has the best accuracy score and also the best, not quite the best, but one of the best variance score amongst the lot. In terms of accuracy score for the 10th out of sample, gradient boosting did almost the best, and it matches to an extent random forest as well as extra trees. So that's really a bird's eye view or a summary view of all the different classifiers and how they perform under different basically in the training, and within training, the average accuracy score, their variance, and finally the actual out of sample performance as well. Okay, with that, that's pretty much the end of our lesson. Before we go, I'd like you to actually run this whole gradient boosting machine. Now, from basically reading this, and have a think about how you would improve the gradient boosting machine. Now, this is pretty much the cutting edge of technology here. When we come back, I'm gonna just explain a little bit, summarize the concept, and I'll introduce to you and I'll talk to you about what we're gonna look at next. So pause the video, give it a try. Welcome back. I really hope that you've actually given it a go in terms of trying to improve the gradient boosting classifier here. Of course, you can also use the gradient boosting regression here, but in our context, in this case, is actually a classifier. Now, this is really the important part that I want you to get at, really, is that going forward, we're going to look at extreme gradient boosting machine. That's really basically the cutting edge of technology right now. The extreme gradient boosting machine was only released 2-3 years ago. That's back in 2014. And ever since it was released, it it is the algorithm or the go-to algorithm to beat competition, to top competition such as Kaggle. So that's really the where we are moving towards after this. But I really want to thank you for paying attention and just patiently follow along and just learning all the different options available, or different machine learning options available. And that's really the important part here, is which of these technology are built upon the previous technology, and also keep tweaking it and try to improve upon it. And when we look at the extreme gradient boosting machine, you will definitely see that, hey, it's really a combination of all of these, and basically making minor adjustment and learning along the way. And who knows, after you learn all of these, and after you've been exposed to extreme gradient boosting machine, or XGBoost for short, it's a lot easier to say, you may be able to come out with another algorithm that actually outperform. Anyway, that's really for the next video. For now, thank you for watching. I look forward to talking to you and sharing with you in the next lesson. Thank you for watching.